is on induction motor drives. So the first part is we'll revise some basic concept on induction motor. Then we'll start with variable frequency drives, and then we look at the voltage source inverter drives and current source inverter drive. Wherever we get to, we continue another time. So the induction motor, we want to just revise some few things about it. So this one is specifically the three-phase induction motor. So we know that the motor has stator and rotor windings, which we are familiar with. So this portion of the slide is just explaining the stator construction. So it's three-phase connected, and there are slots to carry the conductor. So I will skip the construction part. I believe we all remember some few things. So what we will be interested in will be the equivalent circuit. That is where I will go through the operation too. I believe you also understand. Okay. Okay. I think we should start from the equivalent circuit. Then we will take it from there. Okay. Okay. So the three-phase induction motor behaves like has similar behavior like a transformer. So the primary site is the stator, and then the secondary site is the rotor. So we want to look at when you look at the operation, when you excite the stator, a rotating magnetic field is created, which links the rotor and induces a voltage in the rotor. So the voltage that is induced in the rotor, because the rotor conductors are short-circuited, it also produces current flows, and that current also produces a magnetic field. And then the magnetic field on the rotor and then that on the stator will interact to create a torque, and that will turn the rotor. So as it picks up speed, realize that the rate at which the flux cuts the rotor begins to reduce as the motor speed increases. And as it approaches synchronous speed, we know that the rate at which the flux cuts the rotor is very small, right? And the rotor speed can never be more than the synchronous speed. So that is basically the operation. So when you look at it, it basically behaves like a transformer, right? So because it behaves like a transformer, we want to also represent its equivalent circuit like that of a transformer. But we know that the transformer is a static device, but for the induction motor, it's a rotational device. So what we are going to do is we are going to, because the rotor is moving, so we'll model the rotor as if it is stationary. So that is how we are going to look at it. So it will look like it is stationary, so that whatever that all the analysis we're doing on transformer equivalent circuit, we also perform the same analysis on the induction motor. So that is what we are going to do. So now that we are able to, we have this understanding, in the transformer equivalent circuit, it was per phase. So we are going to look at the per phase equivalent circuit. So though it's three phase, we'll convert it to what a single phase, and then we'll do that. So the assumptions are that the turns ratio is what? 1. So it has a turns ratio of 1. So this is the equivalent circuit that we are going to get, right? So this is the equivalent circuit we are going to have. So this represents the stator parameters. So what we have here represents the stator parameters, the leakage flux in the stator, the copper losses in the stator is also represented by RS. And we have our exciting branch. So this exciting branch, we are assuming that the core or iron loss is negligible. So we're only showing the magnetizing branch, so which is this one. So the portion that shows the core or copper loss is neglected, right? So we are just showing only the magnetizing branch. So that is the stator side. And when you come to the rotor side, this is the rotor equivalent circuit. So this is the leakage inductance in the rotor and the rotor resistance. And because it is usually short circuited for the cage induction motor, that is where this short circuit is coming from. So this is the equivalent circuit as standstill. So standstill means that the rotor is not rotating. That is what it means. So you know that the transformer is also stationary. So the frequency on the primary side, the same frequency on the secondary side. So when the induction motor is standstill, the frequency on the motor, the stator side, the same frequencies as we can see, omega E, omega E. But when you're looking at a rotating rotor, the frequencies to be different. So we have to find a way of making their frequencies the same. So we look at them and think that is let me see, let me check if that is here. I think it's here. So we'll come to it. Okay, so that is what we are seeking to do, right? So assume initially that the rotor is prevented from moving. That is what we've looked at. So we have two sets of three-phase windings sharing a common magnetic path that is similar to the three-phase transformer. Since it is balanced, we need to only consider one phase, which we've explained that, and we'll refer all impedances to the stator side and assume a unity turns ratio. So if the rotor is allowed to move, two effects must be considered. So the first one is the EMF induced in the rotor depends on the relative velocity of the rotor with respect to the field. So the relative velocity between the rotor and then the stator field, that is what we are going to look at. So that will tell us the magnitude of EMF that is induced in what the rotor. And the frequency of the voltage produced in the rotor depends on the relative velocity of the rotor with respect to the flux. So the frequency of the induced voltage on the rotor in the rotor depends on what the relative velocity. So we explained that when it's rotating, the rate at which the stator flux cuts the rotor reduces because it's like they are almost at the same speed and the difference is very small. So that means that the frequency of the rotor side will be different from the frequency of the stator side. So what should we do? So we have to modify the rotor circuit so that they will have the frequency on the rotor side to be the same frequency on the stator side so that we can treat it like a transformer. So d phi dt for the rotor reduces because as is against speed. So I think we already know the slip, right? The slip is giving us the synchronous speed minus what the rotor speed divided by the synchronous speed. Sorry, yeah, this is the slip. So the voltage on the induced in the rotor is equal to, that is V2 is equal to the slip times what the voltage induced in the second the stator winding. So we want to, that is the first thing we need to take note of. So the frequency of the rotor voltages and currents reduces to omega slip, and omega slip is given by this relationship, the slip multiplied by what? Omega E. So realize that the frequency on the rotor side is the slip times what the frequency on the stator side. So they are not the same. So we have to redraw this equivalence circuit to ensure that they are the same, right? So before we move to that one, if we make the modification, we know that right now it's now S omega E, right? So which is different from the one here. So this inductance you are going to see its reactance will be multiplied by x let me just say r prime So that is what we are going to have. And this V2 now becomes SV1, right? So this is rotational. So we want to make it stationary so that the frequency on the primary, the stator side will be the same as the rotor side. So that is the next thing we will be looking at. So now let's understand another thing for motoring. So the active power flow in an induction motor. So when you supply power through the stator, that power is the in power. So we know that there are losses in the stator, right? So the losses in the stator, the copper loss and then the core loss in the stator. But in this equivalent circuit, we are neglecting the core losses. So we only have what? Copper loss. So we have copper loss. And when you subtract these losses from the power that was supplied to the stator, will be the power that will move from the stator through the air gap towards the rotor, which is represented by what? PAG, which is the power in the air gap that is transferred from the stator side to the rotor side. So when that power comes to the rotor side, at the rotor side, we also have what? Losses. We have the iron loss and then the copper loss in the rotor, which is represented by P slip. So here we usually neglect the iron loss on the rotor side. So you only have what? The copper loss on the rotor side. Then when you subtract the losses in the rotor from the power that was transferred from the rotor side, sorry, the stator side to the rotor side, that gives us P mechanical. So which is the mechanical power that we have, right? So when you want to know the total output, then you now subtract the mechanical losses from this PMEC to now get the actual output. So this is the power flow, active power flow in the induction motor. So all these that we have, they all have relationships. So we will look at them, right? So now that we know that we need to ensure that this equivalency, you see that the frequency here is different from the frequency here. So how do we ensure that they are both the same so that we treat it like that of the transformer? So that is what we are coming to look at. So we know that the I1 and I2 from that particular diagram, so their phasor magnitudes are different at different frequencies. So they are the same in terms of magnitude, but their phase they are at different frequencies. So because of that, their phases will be different, right? They are different frequencies, so they have different phasor values. So now we also know that the V in, that is in the voltage induced in the rotor, is equal to the slip multiplied by the voltage induced in the stator. That is one of the formulas that we know. So what we want to do is that we want to ensure that this V2 that we have is what is having the same frequency as the V1. So that is what we are trying to do. So we look at the motivation. So again, the magnitude of V1 is at omega E, which is the supplied frequency, and this one at omega slip. So they have different frequencies. So we have to ensure that they all have the same frequency. So let me just draw an equivalent circuit. Let's say this is an inductance. We have this as the resistance, right? And this is our source circuit. And we have this as our V2. And this as our LR. And then we have this as what? RR. And this as I2. So this is the rotor equivalent circuit alone. So we want to see how do we manipulate this so that we can make it have the same frequency as that of the stator. So that is where we are coming to look at. Okay, so that is what we are coming to look at, right? So from this equivalent circuit, so this is the frequency omega slip, right? So from this equivalent circuit, you can calculate for I2. So when you calculate for I2, when you write the equation for I2, it will be V2 will be equal to I2 multiplied by J omega slip LR, right? Plus what? RR. So that is what we are going to have. But we know that this one is what? S V1, which is equal to I2. So what we can do is we can decide to, and we can replace omega slip with this, right? So that means that we are going to have S omega E LR plus what? RR. So now that is what we are going to have. So if we make I2 the subject, that will give us this expression that we are having. So now how do we ensure that they have the same frequencies? So if we decide to divide here by S1 and also divide this side by S1, right? So we divide this side by, sorry, S. So we'll have S cancelling S, and you have V1 to be equal to I2, and then S will cancel the one inside. So you're going to have J omega E LR plus RR over S. So right now we see that the reactances, the frequency of the reactances are the same. So now we can now represent, we can redraw this circuit to now ensure that the frequencies on both sides are the same, like that of the transformer. So that is what we are going to do. So when we redraw, so when we transfer the parameters to the stator side and we redraw the equivalent circuit, we are going to have it as this, right? So this is where the RS we have R over S. So it's coming from this relationship. So that is what we have at this point, right? So now let's now understand some few things. So this R over S can be represented as RR plus RR 1 minus S over S. So if you rewrite if you express, you can express this one in terms of this. So into these two components. So this component represents the copper loss in the rotor, and this one is the mechanical power, PMEC, right? So if you're asked to calculate the output power of the induction motor, and you know the slip, you know the rotor resistance, and with the current through the rotor, you can easily calculate the mechanical output power of the induction motor. And P slip will be given by, so P slip will be equal to I2 squared RR, and this one will be given by I2 squared RR 1 minus S over S. So that is what you're going to have for both. So, and when you sum both, it gives us the power that is transferred from the stator equivalent as stator side to what the rotor side, right? So that is what we are going to have. So this is the per phase equivalent circuit in a simplified form, because we don't have copper losses accounted for. Iron loss accounted for in this particular equivalent circuit. It's very simple, right? So this is the per phase equivalent circuit usually employed for induction motor calculations. Note that the input to this system are calculate the electrical input, the voltage, the current that is supplied, and then the frequency of the supply, and the output is the mechanical, which is the PMEC. So this equivalent circuit, we must know it. We should be able to draw it, and we should be able to use it to analyze, apply it to problems. So let's take note of it. Okay. Any questions? These are there questions? Okay, if there are no questions, then continue. Okay. So we now want to look at the power relationships. So the input power we know already. So since this diagram we have is per phase, everything you calculate here is per phase. So you can now convert it to three-phase by multiplying each of them by 3. So this is per phase. So this power is per phase. So if you want the three-phase value, multiply by 3, right? So we now want to take the equivalent circuit and get useful information from it, namely how do we calculate mechanical output, torque, and losses, and we'll look at that. So the input power is given by this, right? So we are looking at active power flow. So that is what we are looking at. So it will be given by the supplied voltage multiplied by the supplied current, cos of what the power factor of the stator. That is what we are going to do. And since this is per phase, you multiply by 3 to get the three-phase input. And some of the power is dissipated in the stator resistance. So which would be the stator's current times what? The square of the stator's current times the rotor, the stator's resistance. So this is per phase. So if it's three-phase, you multiply by 3. So the power that is transferred from the stator through the air gap to the rotor is given by this expression. So since we are neglecting the iron loss on the stator side, the power is going to be the power in P in minus what? P RS. That is the power the copper loss in the stator resistance. So that is given by this expression. So let's take note of this. It's going to be relevant later. Then another way you can do is you multiply the stator's this will be, so let's come to the equivalent circuit, right? See, at this point, this is where we have V1, and then we also have I1 at this point. So what you do, so this since this is close, this is almost at the stator side, we are going to, sorry, the rotor side, we are going to use the power factor of the rotor to do that calculation. So that is the difference between this one and then this one. If you've observed, there are differences in them. All right. Okay. So the power that is dissipated in the rotor circuit is given by P slip, which is given by this expression. And since we know that V2 is SV1, then you put it there. So the P slip is equal to the slip times what the power that is transferred from the rotor side, sorry, the stator side to the rotor side, which we call the air gap power. So that is given by this same relationship. So you have to take note of this expression. So when you know the power that is transferred from the rotor, the stator side to the rotor side, you multiply by S to get the power loss in the rotor, which is given as P slip. And all these are per phase values. So let's take note. And then for the mechanical power, it is given by the power in the air gap minus what? The P slip. So when we do the substitution, you are going to get this relationship for the P mech. So let's take note of these formulas. They'll become relevant when we are solving problems. Okay. So that is we are looking at that for the cage, right? But when you look at for wound rotor, it is possible to extract a large proportion of this. So excluding this portion. Okay. So we know that we can for the wound rotor, we can assess the rotor resistance through the slip rings. So we can what this is saying is the losses, this P loss that is in this power that is lost in the P slip, we can extract it through the slip ring. So you can connect loads to it, or I don't know how it is done, but you can connect something through the slip rings to be able to get make use of this P slip, which is the power loss in the rotor. And for a page 2, they also have similar expressions. So you just have to know that for the wound rotor, you can access the windings and extract its power. But for the page, everything is shorted, so you cannot have access to the windings. So that's the difference between the two. So the P slip must be kept below or at its designed value to avoid the rotor from overheating, because this is a loss, so it causes heating. So you have to ensure that it's always below its value, or it shouldn't go above the rated. So so you have to take note of that. So normally, unless the machine is producing very little mechanical power, the slip must be kept very small to avoid the rotor overheating. So we usually ensure that the slip is very small to prevent the motor from overheating, because we know that the power that is transferred from the rotor side, we know that P slip is S times what? PAG. So that is what we have. So if slip is very big, you realize that much portion of the power that is transferred from the stator to the rotor will be dissipated in the form of heat. So which will lead to overheating of the rotor. So we want to always ensure that this slip is very small at rated values. So this is why the speed control of the induction motor is not straightforward, because the slip. So if you want to control the rotor speed, so omega r is given by 1 minus s omega e. So if you want to control the speed, realize that this is the supplies frequency. So you can change this one, but the slip to be also, you have to also have control the slip, right? So if this slip is very big, it will give us high losses in the rotor circuit, and it will also give us small rotor speed. So that is what we need to take note of. So now that we are able to calculate the power, the next thing is the torque, right? So how do we calculate the torque? So the torque is simply calculated by knowing the mechanical angular velocity, which is given as Vm. So we know that we have electrical speed and mechanical speed, and they are always related by this formula that we have here. So the mechanical speed is given by the electrical speed divided by number of pole pairs. So this is something we have to take note of. So when you get your electrical speed divided by what? P, to get the mechanical speed. So we have to take note of this. It's very, very important. Okay. So now that we know how to convert from electrical speed to mechanical speed using this relationship, then we can go ahead and we'll calculate for the torque. And then the torque is the mechanical output power divided by the mechanical speed, right? And we are saying the values we calculated by per phase. So because we are looking at the total torque, we are looking at the three-phase torque. So we have to multiply the mechanical output power per phase by 3, and we divide that by what? The mechanical speed, to get the torque. That is what we are going to do. So this is also one of the expressions we have to take note of. So that, and then another expression we can also extract from the equivalent circuit is that the PAG, which is the power transfer from through the air gap to the rotor, is per phase is given by this expression. So RS RR over S multiplied by IR squared. So this gives us the power that is transferred from the stator to the rotor side. So this is also something we have to take note of. Okay. I think we've seen this already. We've also seen this already. And the three-phase power. So this is the phase value. So you multiply by 3 to get the three-phase power. So that is something you have to also take note of. So now that we know the three-phase mechanical power, we can divide this by what? Omega m to get the torque, right? So that we will look at the torque expression. So we've also seen this relationship before, the ones relating the rotor current to the voltage. So the one that we had, SV1 is equal to I2 JS omega E LR plus R, where we divided through by S. So and we made this the subject. So this from this expression, right? So we make I2 the subject and you divide through by S. You are going to come up with this expression. So this is the current that will flow through the rotor circuit. So if you're interested in just the magnitude, then we know how to calculate the magnitude, which will be given by this relationship. So at any point, if you don't get anything or if I'm moving fast, please let me know so that I will take my time and explain. Okay. We've also seen how to convert from electrical to mechanical using this relationship, right? So we know that omega R is given by 1 minus S omega E. So this is electrical. So we want to convert it to mechanical, then you divide this by what? P A by P, and this is omega R mechanical. So this is where this is also coming from, right? And the torque to can also be given by this expression. So now, where is this coming from? So we come back to the relationship we had here, this relationship that we have here. So that is what we are using to do the conversion. So the torque that is developed by the motor is given by what? This expression. So that is what we are going to have. This expression that we are seeing here, we know that the power, the three-phase power is given by what? 3 times IR squared PR over S. So we need to divide this by the speed. And the speed, we want the mechanical speed, right? So the mechanical speed should be omega E over P. So you realize that the P will go up, S will come down, and then we'll have this expression. So this one is something you also have to take note of. So when we make I2, IR square the subject and we substitute here, you also get this expression. So let's take our time and then go through. So there are different expressions, but they are all pointing to the same thing, but we are just writing them in different ways because we will need them in the analysis to understand some things, right? So let's take note of them. Let's take note of this one and then the other one. So these are the torque equations. So when an induction motor is connected to a fixed frequency, fixed amplitude voltage, we know that P is a constant because the number of poles is constant after the machine is constructed. So P is constant. R is also constant. Resistance is constant. Inductance is also constant. And then the speed is constant. And because if you look at if the stator drop is very small, V1 is approximately the same as V as the supply voltage. So we can also make that assumption, right? So now when we make that assumption, we can say that if we come back to this same expression that we have here, we come back to this the expression we have here, we can simplify this expression, right? So let's see we decide to multiply through by S. So you decide to multiply through by S squared rather. Let me put it that way. So you multiply here by s squared, you multiply there by x squared. So it's just like you multiply here by s and you multiply here by s, and when it comes out here, it becomes what? Over s squared, right? So that is why we have s squared here. So that it's like everything is balanced. So you try to, so let me just say you are trying to factor 1 over s out. So when you factor 1 over s out of this one, and you want it to also affect this one, then at the end of the day, you have 1 over s squared at this side. And this one will be multiplied by s squared, and here s will go away. So you have this small s canceling one of this, and then that one goes up. So this expression we are arriving at to be 2 and 3p SV1 squared RR over omega E square. We have RR squared plus S omega EL R prime squared. That is what we are going to have. So we've just we just explained that all the other parameters will be constant. So this is constant, this is constant, this is constant. So we can represent everything with a constant multiplied by the slope. So that is what we are saying at this point. So that is what has been done here. So this k that we are seeing here is equal to 3p v1 squared r from this expression. That's where this is coming from. So we can come to a conclusion that the torque is what? Proportional to the slope. So that is a conclusion we can draw from this expression. So we can see that the torque is proportional to the slope. So we want to see how the torque varies with slope. Please, I hope we are followed. This particular relationship that we are looking at is very, very important. Yes. That is what we are going to use for most of the design and then analysis. All right. So we can plot torque against slip from this particular expression. So it is, however, more useful to substitute this as we substitute the slip with this expression, and then we plot the torque against omega r rather. But whichever one you do, you will still get a similar curve. So this is the torque against the rotor speed omega r. So that is what we are going to have, right? So this is the relationship we have, the torque against speed curve of an induction motor. So this is what we have. So this is the starting torque. We have the maximum torque. And then we have the no-load torque at, so when you go down, it will give us a value of 0, right? So this is the curve you are going to have. And when you look at this portion, so this portion, you see that it's linear, it's the linear region. So most of the times, mostly the induction motor operates when it's at full load, it operates in the linear region. So this is where it's going to, or it's going to operate in the linear region. So what happens at low slip? So at low slip, that is where it will be operating. So you realize that this one, this curve you see, so it's omega r is equal to 1 minus s omega e. So you realize that when slip is 0, what happens? When slip is 0, we have omega r to be equal to omega e. That is at this point. So at this point, we have slip to be 0. And when slip is 1, realize that the speed is 0. At this point, the slip is 1. S is equal to 1. And then S is equal to 0 at this point. So you realize that as the motor increases speed from 0 to the synchronous speed, you realize that the slip also keeps on reducing. So at this point, around this region, that is where we have what? The low slip. And this region, the slip is quite high, and then medium is within this portion where it is almost maximum. So let's do the analysis. So when the slip is low, as the rotor frequency approaches the applied stator frequency. So that is where the slip is very small. So I've shown you where it will be. So, and in the figure that we just look at, it appears to be what? A straight line. So that is what we need to take note of. And we also remember that V1 is approximately Vn. So in this particular region, so from this expression that we have here, because the slope is very, very, very small, r squared be far, far out, far, far greater than this, because you are scoring slope that is almost 0. So this value will be very small compared to this, so we can neglect this. So when we do that approximation, we are going to have this relationship for the torque. So we can see that is from here, right? I think this is where I wrote that expression. So from here we can make that as approximation that the torque could be this is very small, so it goes to almost 0, and we have so for the three-phase one, it will be three-phase Vs V1 squared R over omega E R squared. So one will cancel the other one. So that is what we are going to have, right? So which is, so let me write the same expression here. So we are going to have three-phase V1 RR. This is S over omega E RR squared. So one cancels one. So we are left with three-phase SV1. This is squared rather. So over omega E R. So we just want to express this as omega slip. So when we multiply the top by omega E and multiply the bottom by omega E, you are going to have 3 S omega E V1 squared over omega E squared R. So realize that this represents omega slip. So we can put it there. So this expression that we are having here is per phase. So it's per phase. But when we're looking at the three phase, we need to put 3P there, right? So from this relationship, we can see that the torque is what? When the slip is very small, very low, the torque is proportional to omega slip, and that happens in the linear region of what the torque speed curve of the induction motor. So it happens inside this region. That is when that happens, because at that point, that is where the torque is what? Very low, very small. Please, do we understand? So this approximation, this what we have is very, very important. It's a very important conclusion, especially for our work on control of variable speed drives, as we need a control parameter that is proportional to torque. So that is what we have here. So this relationship is very, 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 very important. This relationship that we've arrived at, it's very important. If you've forgotten the rest, but this one there, you have to remember it, because the variable frequency drives that we are going to do. It says this is a relationship we are going to use for that. Okay, so note that gradient of this curve can be altered by changing Vs. The magnitude, that's the magnitude of this particular formula that we have. So this represents what? The gradient, right? So this represents the gradient. So it can be altered by what? First, by changing Vs. So when we change Vs, how do we, so we can change the Vs by what? Using a variac or a three terraces to vary the input voltage. That is one way you can do it. And R can also be changed, right? So if it is one rotor, we can connect external what? Resistance through the slip rings, but so that we can try to change the torque. But you realize that doing this is making it inefficient because the you know that when you add resistances, what happens? If you add extra resistance, you're increasing what the losses, which will lead to a lot of heating. So adding resistance will not be the best option. And also, changing VS will also it's going to affect the flux too. So when you change VS, it's going to also affect the flux that is in the circuit. So realize that changing the VS or changing the resistance will not be the best option to vary the torque, right? So that means we need to look for better ways of doing it. So now we continue. So when you are required to do performance calculation on induction motors, it's essential to understand the following observations: the voltage and the current. So the concept of the per phase equivalent circuit assumes the machine comprises three independent electrical windings fed by a single phase voltage and a phase current. In reality, machine will be star or delta connected. So this connection affects the voltages and current that are given for our calculation. So this equivalent circuit just shows per phase values, but the actual machine is three phase. So is that star connected or delta connected? So if you are giving the parameters, they will most likely be three phase parameters. So we should be able to convert them to phase values. So when it's star, we know that for star, the phase voltage is equal to the line voltage divided by √3. And if it's delta, the phase voltage is the same as the line voltage. So we know how to go about the calculations. So they are usually line voltages at rated conditions. So that is rated load torque and a rated speed, and that's the rated mechanical output. So what is given to us is the line voltage and rated condition. So we should be able to convert it to phase value depending on whether it's star connected or delta connected. So we should take note of that. So if it is star connected, the phase value is equal to the line voltage divided by √3, and the phase current is the same as the line current. But for delta connected, the line voltage is the same as the phase voltage, and then the phase current is the line current divided by √3. So I think we are familiar with these. So we know how to calculate the power. So we calculate for these are phase values. So if you want to do three-phase calculations, then we know that this is representing phase value. So what is the phase voltage? The phase voltage of star is what? Line voltage divided by √3. When you do the substitution and then you perform your expression, you come up with this, which I believe you also know, right? So, and if it's delta 2, you arrive at the same expression. So I think we are familiar with these ones. The next thing we have to look at is the speed, frequency, and slip. So note from before that, so we should take note the mechanical speed, right, in rats per second. You have to divide by number of pole pairs. So let's take note of this. Let's remember this. Okay. So we are usually given rated speed in RPM and then rated stator frequency. So if you are given a parameter, these are the parameters that will be given to you. And we have to infer the number of poles and calculate the rated slip. So we are given the rated speed and then the stated frequency. So we have to infer the number of poles and use that to calculate what? The slip. So that is what we are given. So we take an example. So you should, however, be aware that the rated slip is very small. So the typical value is less than 0.1, right? Typically, it's less than 0.1. So for example, if you're given this as the rotor speed and this as the frequency, so how do we calculate? How can we infer the rotor poles and help us get the slip? So we know that this is given in what? RPM, which is the mechanical value, right? So it's given in RPM, so we convert it to rad per second. So when you convert it to rad per second and you equate it to this particular formula that we have, 1 minus S multiplied by omega E over P. We know that omega E is given by what? 2 pi F. So that is where this is coming from. And you can, so we have, you have this portion to be equal to this. So if we say that we want to always keep value less than 0.1, then you can infer the number of poles. So usually when you are giving the this speed and the frequency, is very easy to get it done. So another way you can do is, we know that ns is what 60 f over p. So you just substitute in the value if you don't know p, but you can get this is the trick. So usually the rated speed and the synchronous speed are not far from each other, so they are very close. So for if this particular speed that we are giving, right, this particular speed we are giving, so we know that it's 1480. So what value of p will give us a synchronous speed that is close to this value? So now we know we are going to have 60 times what? 50, that is 3000 divided by p. So what value should you choose so that it will be equal to this value? So if you pick one, this should be 3000, which is far from what? 1480. But when you pick two, this gives us 150, 1500. 1500 is close to this value. So we know that the number of our pole pairs is going to be 2, right? So you can just do some of these basic analysis to infer the number of poles. And you can use that to get your slip. Okay. All right. Now we look at the power and then the torque. So if a power rating is provided, it will be the total output mechanical power. So let's take note, the power rating that is given, it is the total output mechanical power. And this is 3-phase. So you should be able to convert this to a single phase. And the torque, so if you have to calculate the rated torque, then you're going to divide this power by what? The rated what? Mechanical speed. So if it's giving us electrical, you convert it to mechanical. So I know by now, we know how to convert from electrical to mechanical. And if you have mechanical, how to do the conversion. So this is what you use to calculate for what? The rated torque. So let's take note of this particular expression too. Okay. Then, so let's take examples, right? And see. So before we take examples, if you have any question, please let me know, so that I can address it before we take the examples. Any questions? Okay, since there are no questions, let's take the examples. Okay, so this example, the per phase equivalent circuit for a 4-pole 415 50 Hz induction motor may be approximated to a magnetizing inductance of 600 millihenry and a rotor resistance of 0.453 ohms. The rated speed of the machine is 1480 RPM. To calculate the rated output power, rated torque, and rated current. So let's look at this first example. So we've been given the model of the per phase equivalent circuit. So we are told that we should neglect everything except the magnetizing inductance and then the rotor resistance. So that means that the stator inductance will be neglected, stator's resistance will be neglected, rotor's inductance will be neglected. So we only have the magnetizing inductance, right? And then the rotor resistance. So this will be Lm, and this will be R over S. So this is what we have. So, and we have our supply voltage. This is, let's call this I1, maybe we can call this I2, which is the rotor resistance, and then this is probably IM. So however we name it. So that is what we are going to have. So the question says we should calculate the rated output power. So the rated output power is the mechanical output power. So that is what we need to calculate. So first of all, so we saw that PMEC. So that machine is three-phase, so we have to make it three-phase. It's going to be 3 times IR squared RR into 1 minus S over S. So remember seeing this example. So this phase multiply by 3 to get the three-phase value. So from this relationship, we need IR and we need slip. So we need to calculate these two values and then come a substitute. So how do we calculate the slip? So we've been given the frequency, we've been given the rated speed of the machine, which is given by this. So from here we can just know what the synchronous speed will be, and then you calculate for the slip, right? So slip is given by ns minus nr over ns. So if the number of poles have been given to us already, so from here we know ns, which is going to be 60 times 50. So ns is 60 times 50 divided by 2 because the pole pairs is 2. And this one gives us what? 1,500. So you come and substitute 1,500 minus 1,480 over 1,500. So this gives us the slip. So we know how we know the slip now. The next is to get IR, which is the current. So let me make it IR. So from here we need to take a loop to determine IR. So this voltage is also given, but is the three-phase value that is given. So we need to convert this three-phase value to per phase value. And in Hashimoto, if you are not told anything, just assume it is star connected. So unless you are specifically told that it is delta, if not, just assume it's star. So we are going to convert this to phase value. So we divide this by √3 to get the phase value here. Then you take the loop, right? So if I call this VS, so when you can take a loop, and when you take the loop, you have VS to be equal to IR RR over S. So you make this the subject. So that gives us IR to be V S multiplied by S over R IR. So this one, when you divide this by √3, you get a slip is known, RR is known. So you know your IR. Then you come and substitute to get your mechanical output power. So that is how you go about it. Please, any questions on the mechanical output? Okay, so we'll go through the solution, but I just want to take my time and explain. Then the second one is the rated torque. So since we know the rated output, so we calculate for the rated torque, right? We've been given the rated speed as this. So we convert this to what? Rats per second. And then we divide the rated mechanical output by the speed in rats per second, and that gives us the torque. And then the rated current is the current that is from the supply, which is given by, let's say, IS. So this current is what we are interested in. So we know IR, so we need to calculate for IM. But because IM is an inductor, the IS is going to be the vector sum of what? IM and then IR. So IS will be vector sum of IM plus IR. So since we are interested in the magnitude, we know how to calculate the magnitude, which should be square root of IM squared plus IR squared. So we can take a loop here to determine IM, and then we have IR. So let's just go through that portion of the solution, then we'll come and continue with the rest of the problem. So the first thing that is calculated is the slip. So we understand how to calculate the slip. Then this is the phase value. We wrote the expression for the IR, you do the substitution, and then you obtain the current, right? And the P naught, which is the output, we wrote the expression, so you do the substitution to get the mechanical output power. And the last thing is the torque. So this the speed was converted to rats per second by multiplying through by 2 pi over 60. So that is the torque, and this is the magnitude of Im. So it's going to be V S over what? Omega E Lm. So we know omega E is 2 pi F, right? So the frequency was given as 50, and the inductance was 600 millihenry. So when you convert it to Henry, you get 0.6. So this is at the magnitude, and we know IR already. So the S is going to be given by this expression. And that's how we go about the first part of the question. Please, are there any questions on this? Okay, so let's continue. So the second part of the question says, now let's move on to the next part of the question. The induction motor we have been working on fits a load, which can be characterized by this particular equation. So the load torque is given by this relationship, where omega R is the mechanical speed in rats per second. So we should calculate the speed and torque developed when the stator voltage is reduced to 380 volt, then to 250 volt, while still at a rated at the frequency of 50 hertz. So that is what we are going to do. So we know that the motor torque must be equal to what the load torque. So TE must be equal to TL. So we already know TL. So what is TE? So TE, we saw that TE was given by this expression. TE is approximately equal to 3 times the number of poles multiplied by Vs squared over omega E squared RR omega slip. We saw this so we saw this relationship, right? So we are going to make use of this relationship. So this is our TE, then we equate it to this, right? So that is what we are going to do. So we are going to equate TL to TE. So omega S here, I'm sorry, Vs here is what? The phase value of this one. So you can calculate for the phase value, and you know the P already to be 2. We know the frequency is 50 hertz, so we know this one. Omega slip. So you see that this value, the values that we have here, the omega slip here is what? Omega R, omega slip is omega E minus omega R. So we can substitute wherever we see omega slip, we are going to put one. Omega E minus omega R. Then we substitute the values and equate to this one. Then we solve for what the values. So that is what we are going to do. So that is how we go about solving this particular example. And when you change the voltage to this, then you do the same thing. So that is the next part of the question. So which is this expression that we have. So I believe now we know where this is coming from, right? And he has just done some substitution. So let me just explain what happens here. So we know that V phase is what? V line over root 3. So if you square this and also square this, you're going to get V line squared over 3. So when you come and substitute here, you see that this 3 cancels this 3, and P is 2 already. So you just put 2 there. That is what he has done. And omega slip is also omega slip. Let me write it again. It's omega E minus omega R. So omega E is 2 pi F and omega R is here. So we do the substitution. So that is where this is coming from. It's not any strange thing, right? So now that we have this, when the line voltage is 380, we substitute and we equate it to a TL and we calculate for omega R. So that is what is happening here, right? So you just do the substitution and the rest is make omega R the subject and then you get. So this is what this is what we have for omega. Then when it's but you have to convert this to what what's the name, the mechanical, right? So since we need to convert this to mechanical, let's take note of the P that is there. So this is omega R. So we have to convert it to mechanical speed. So this is in rad per second. So if you want it in RPM, you multiply by 60 over pi and divide it by what? P, which is number of poles, pairs, to get the speed in to get the mechanical speed in RPM. So that is what is done here. So this 2 is the number of pole pairs. And then this portion is helping us convert this speed to RPM. So that is what has been done here. And when you know the speed, then you can calculate for the torque that is required at that point. Then you change the voltage to 250, you do the substitution, then you go through the same thing. Any question? That is how you go about solving this particular problem. Any questions? Please, are there any questions? Okay.
No question.
All right, thank you. So let's look at the next problem. It says a 4-pole 3-phase cage rotor induction motor has the following parameters referred to the stator side. So RS is 0.1 ohm, LS 1 milli, LO is 4 T millihenry, LR is 1 millihenry, R is 0.2. All values are per phase, assuming a star connected machine. The machine is fed from 415 volts, 50 hertz supply, and the slip is 4%. Ignoring the effects of RS, LS, and LR, determine the rotor speed, the torque, and the power dissipated by the rotor resistance. So we are asked to neglect RS, LS, and LR. So what would be the equivalent circuit? So the equivalent circuit will reduce to just this, and then RR over S, and then this is L naught, which is the magnetizing part. Then you have this as your supply V phase. So this will be the equivalent circuit. So he has just simplified it for us by letting us ignore the other parameter. So the first is to determine the rotor speed. So, and the torque, and then the power dissipated by the rotor resistance. So how do we obtain the rotor speed? So let's look at it. So first of all, we need to we need to obtain this current, right? And we can determine this current. So first of all, let's start by looking at the power that is dissipated. That one is straightforward to do. So which is in the rotor resistance, which will be given by I2 3 times what? IR squared RR. So that one is straightforward. So we can determine that, right? So to determine the rotor speed, So we've been given the slip. So we know slip is omega E minus omega R over omega E. So since we know the slip, we can calculate for omega R. Then we will get it in electrical value. So this will be the electrical one. Then we convert it to mechanical. So from when you make omega R the subject, you get omega R to be what? 1 minus S omega E. So if you want it in mechanical, then you divide through by whole pair to get it in mechanical. So that is how you go about solving this one. Then the last one is the torque. So torque we know 3P V phase squared over omega E squared RR. So we know this already. So we go ahead and do the substitutions, and I think we are going to also get the torque. So that's how you go about solving this particular example. And you have told that the supply current is now reduced to this value, and both load torque requirements are the same. So we should make the same assumptions and determine the rotor speed, power dissipated in the rotor, and we should discuss that whether neglecting this will affect the calculations too. So that is what we need to do, right? So we'll go through with the same expressions, we'll go through the calculations. Okay. So we have this equivalent circuit here, and the first thing we need to do is get the IR so that it can help us calculate the power loss in the resistor. So that is what we are going to do. And we can also calculate the torque. So all these values have been converted. So calculating for IR, we've seen the formula already, right? So you just take this loop, which is Vs is equal to IR multiplied by RR over S. So we know S already, we know RR, we know Vs, which is the phase value, and we make IR the subject. So when we do that and substitute in the values, we are going to obtain 48 amps. So now that we've gotten IR, the P loss is basically the P slip. So that is what you calculate here. So this is the P slip. And then this particular one is talking about the power that is transferred from the stator through the air gap to the rotor side. So that is this particular one. Then, because we are always interested, we want to calculate the the torque at that point. We need the mechanical power, and we said that the mechanical power is PAG minus the slip. So we subtract this one from, we subtract the slip from the P slip from what the PAG to get the mechanical output power, and we divide that by what the speed to obtain the torque, right? So the speed is given here. It's given as this 1 minus S times what the slip. That is what you will use, and this is in RPM. Convert it to rad per second, and divide the mechanical output power by the speed to get the torque. So that is how you go about the first part of the question. So realize that the formulas that we saw, we are just making use of them. That is all we are doing. Okay. Then the B part of the question, we are told that the supply is now reduced to 346 volt, but the load torque requirements still remain the same. So we should make the same assumptions and determine the motor speed and then the power dissipated in the rotor resistance. So that is what we are supposed to do. So that is the next part of the question. So when we calculate the phase value, divide this by root 3 to get the phase value, right? And we know this formula already because we know that P mech is 1 minus S times what? PAG. So you just make, if you make PAG just that, you are going to obtain this. And the mechanical power, since we are told that the load requirements are still the same, the mechanical power is going to be equal to the torque multiplied by what? The speed. The load, the torque requirements remain the same. So the torque that we calculated from from the first part of the question, which is 220, will still remain the same. So the output mechanical power is going to be 220 multiplied by the rotor speed. So that is what we are going to have, right? So, and we can also determine the rotor speed. So the rotor speed is also given by what this expression, which we are familiar with. So, which we are familiar with. So here, when we introduce 2, so this is 2. So when you put it and simplify, you're going to obtain this. So wherever we see omega r, you can put 1 minus what? S there. 157 multiplied by 1 minus S there. So P mech will now be equal to this. So we're just making substitution. And you will obtain this expression. Then you come and substitute into PAG. And that is what you will do. So since the input is still the same, the input has not changed, right? Just that the voltage has reduced. So because the voltage has reduced, it's also going to affect the value. So that is the difference here. So the voltage is the only one that has reduced, right? And everything is still the same, and we are neglecting the other parameters. So the PAG, we know that is given by what? The 3 V phase. Okay, let me just see. Is given by this expression that we have here. This particular relationship. This is what we have. So this is what we are having at this point. There's a relationship for PAG. So we can go and then also put it there, substitute in at this point, right? So that is what we are basically trying to do. So what are we going to have? So we are going to get it's given by 3 VS IR. So this is what this is what we will have. So what is IR? IR is what? VS over RR over S. So we make that substitution. So when you make that substitution, you are going to get this particular expression. So this is what you are going to get, right? Because you have VS squared multiplied by 3 divided by RR over S. So that is what we are going to have. But since the input power is only the input power that has what reduced, right? So since the input power has reduced, I keep saying the supplied voltage is what has reduced. We know that when you come back to the question, it says that all the assumptions are the same, right? Just that the voltage has been reduced. So if the voltage has been reduced, so it's going to affect the slip. It's going to affect the slip because we know that the slip will be affected because we have changed what the voltage. So that is what will happen at this point, right? So that is what will happen here. So because of that, we need to calculate for a new slip. So how do we calculate for a new slip? So since we know the P mechanical to be given by this expression. Okay, let me just, I don't know whether I should, okay, let me try and write. So we know that the P, okay, let me write it here. We know that the PAG is given by 3Vs squared over R over S. So we can make the substitution here. This is also equal to P mech over what? 1 over S. So we know P mech is given by this, which is 303,4,540. 1 minus S divided by what? 1 minus S, right? So this cancels this. So you have this to be equal to whatever that is here. So so Vs is what the phase value, which will be 346 over root 3, which we got to be 200. So we substitute that one. We also substitute the value of RR and we calculate for what? The slip. So when we get the slip, the new slip, then we can go ahead and then calculate for the power that is dissipated. All right. So when we get the slip, we can know the P mech 2. And with that, we can calculate for the speed, and we can also calculate for the power that is lost in the resistance. That is how you go about it. I don't know if that makes sense. Please, is there any question? Maybe if I should take the second part of the example again. Yes. Should I take it again? Okay, please, if you don't have any question, then let's continue. I think that is how you go about the second part of the example. So it's not any big deal. All right. So the third part of the question says we should calculate the starting current for the motor described in Q2 when it is supplied from 415 volts, 50 hertz supply. The same machine is connected to a variable voltage frequency supply, which is controlled so that the magnetizing current is maintained constant and the minimum frequency step of this inverter is 1 hertz. We should calculate the starting current for this drive system. Okay, so we are referring back to example 2. So we asked to calculate the starting current for the motor, and we are told that it's now supplied from a variable frequency supply, and the the field current is controlled to be constant, right? And then the minimum frequency step of this inverter is 1 hertz. So we should calculate the starting current from this drive system. So which is basically we're interested in getting IS, that is the current as starting. So that is what we are interested in. So there is the same equivalent circuit we are going to make use of, right? Because we are just making use of the parameters from the this particular example. So the equivalent circuit is going to be the same. So is I'm coming. Okay, please let's continue. Okay, so the question is in two parts. So the first part is we should calculate the starting current for the induction machine described in question 2 when supplied from a 415 50 years supply. And that is the first part of the question. The second part says the same machine is connected to a variable voltage, variable frequency supply, which is controlled so that a magnetizing current is maintained constant and the minimum frequency step of this inverter is 1 Hertz. We should also calculate the starting current from for the drive. So the first one is we've been given the parameters here. So these are the parameters that we are given. So this RS, LS, L naught. So we've given all these parameters. So what we have to do is to calculate for the supplies current, right? So we draw the equivalent circuit of this one. So the equivalent circuit, we know this is resistance and have this branch, the induct resist. No, let me make this inductance and then the resistance. So this is the current that we want, IS. This is RS, LS, and then this is L naught. So this is what we have, right? So we can calculate for this IS. So that is what we want. That is what we want to do. So now, so so from here, this is the inputs that we have. So we need to get this and then the current outflow here and then the current outflow. If you're able to determine that, then we'll be able to calculate for IS. But we can also take loops, right? To help us do that. So if we take this loop, we don't know the current here. If you also take this loop, we don't know the current in this one. We also know the voltage that is applied across them. So how do we go about it? But let me see if you've been given information here that will be relevant. Okay. Okay, I don't see any other information. So then this one, so what we have to do is we just need to combine the impedances, right? So this and that are in parallel, we combine and then add it to whatever we have here to get the total impedance and divide the supplied voltage by that one. Then we find the magnitude. I think that is the best thing we can do right now. So we put this and that are in series, which is in parallel with this. So we know they are this will be complex number, right? So this will be complex, this complex, and this will also be complex. So we put this and that together in parallel, and the combination will be in series with this one. But everything is complex, so we just have to know how to punch it on our calculators, and that gives us the total impedance. And IS will be the VS over the total impedance that we are going to see here. So when whatever we get, then we can now calculate the magnitude of it. So that is how we go about the first part. Then the second part, we've been told that this particular one, it is the second part is fed from a variable voltage, variable frequency. We are told that this is the step frequency, right? So for that particular one, we know this one and then this are in parallel, right? So if they're in parallel, then the voltage that is across this one, the voltage that is across this one is going to be the same. So that means that the voltage here is Vm, which will be 2 pi the frequency times what? Lm, right? So since the frequency is giving us 1, we know Lm, we know 2 pi, then we can get the voltage here. So we get the voltage here, we can calculate the current here. We can equally calculate the current here, and then that gives us the vectors, the IS will be equal to the vector sum of both. And we can use that to get the magnitude of ISO. That is just how we go about it. So let's go through the solution together. So now, since this is a starting, right? So since this is at starting, we know that at starting, the slip is 1. So the equivalent circuit we have here, this S is going to be 1. So that is what we will have. So when the S is 1, this is the equivalent circuit we have. We've just explained that. Okay, he has ignored the magnetizing branch. So if you ignore it, what are the impedance that I mentioned here? If you ignore this one, this and that will not be parallel again. So this and that one will be in series. That's the assumption he made. So I don't know why he made that assumption. I'm thinking that he might neglect it because I am will be very small. So that's what I'm thinking. So if we neglect this one, then the resistances will be in series, the inductances will also be in series. So we just add them, get the complex value, which is the impedance. So we divide that by we divide the phase value by the impedance to get the starting current value. So since we are interested in the magnitude, that's why we are using only the magnitude. So that is the first part of the question. And the second part, he neglected the RS, LS, and then also LR2 was also neglected. So he calculated for IM at this part, he calculated for IM, and the VM at that particular voltage was also calculated for. So since the frequency is 1, that is where it is coming from. The impedance is going to be 2 pi f L m. So Lm was giving us 40 milli, which is this one. The frequency is known, and we have this particular, this is the 2 pi, and the current value was also calculated using this particular expression. So that is at 50 hertz. So that was the magnetizing current. So now that the supply frequency is at 100 hertz, then we can calculate for the new value. And still, since it's still a starting current, we will use that particular voltage to get this one. So the approximation, I don't know why he's making such an approximation at this point. So you have to go and check why he's making that approximation at this point. But that is what is, and that is how you go about it. So I'll find out why he's making that approximation at this point. So at higher frequencies, he's neglecting why he's neglecting these values. So I'll try and find out why that is so. Okay, any questions? We have one more question. Yeah, and I saw a number of them. So we have 2 more examples. I think so. I think we should stop here, and then the rest of the examples we can try them on our own. If we now have issues, then we'll tackle them later. Right. So the next one is on the variable FET induction motor drives. So the voltage source converters. So I think that one will continue another time. We just had 2 hours, so it's almost 6. But if you want us to continue, then you can continue. Should we continue? Please, should we continue? Okay. So please, should we continue with the variable FET drive? Please, should we continue? I want to know if we have to continue, then okay. So let's continue with the variable speed um induction motor drives. So we'll just lay the foundation and then next time we'll continue. So three-phase induction. So this is basically the equivalent circuit that we have. So this is the variable frequency induction motor, the equivalent circuit. So when you look at the power convert, this represents the induction motor. We have a speed feedback coming to the control circuit, and for the power electronic device, we have a rectifier and an inverter. So definitely there'll be a DC link here. So you take the three-phase AC, you rectify it to DC, and you use PWM inverter to modulate the output frequency and voltage and feed it to the induction motor. So that is what we are going to be looking at. So about 60% of the world's electrical energy is consumed by rotating machines, and 90% of it is consumed by induction motors. So they consume much of the energy that is generated, right? So these are their power ratings. So I'll skip. Then we come back to the equivalent circuit that we are using. Right? So this is the equivalent circuit we are still going to use, right? We've seen this already, and one important point that was made was that for to operate with good rotor efficiency, the slip must be kept small because the rotor losses were the slip times the power that is transferred from the stator to the rotor. So we must keep the slip small so that we operate at high efficiency. and variable frequency operation is required. So if you want to change the rotor speed, then you have to change the synchronous speed. So omega r is 1 minus s omega e. So if you want this to change, then you change this one. So it's kind of like a way to change the rotor speed. So, and we have to ensure that this slip is constant at the rated load. If this is constant, then we can, anytime you change omega e, then this will change in the same proportion. All right. So why variable voltage? So let's understand why the voltage will also be variable. So we think we are familiar with this particular curve, which is flux against MMF. So consider phi g to be the air gap flux level, and then phi g is controlled by the MMF, and we know the MMF is proportional to the current, right? And the current that will flow will also kind of have a relationship with voltage. So if you vary the voltage, you vary the current, you can vary the MMF. So that is by varying the magnetizing current. So that is how we are able to change the flux. So if iron saturates as IM is increased above its rated value, so if we increase the magnetizing current above the rated value, the core is going to what? To be saturated. So a large increase in IR will only give a small change in the flux when it's saturated. This we know. And we also know that the torque is proportional to the flux times the rotor resistance, because we said that the torque is generated as a result of the interaction of the current in the rotor and the flux generated in the stator. When the two interact, that is when the torque is generated. So we can also say that the torque is proportional to the flux times the current through the rotor. So ideally, we want to control the flux to be as large as possible. So as we increase the flux beyond each rated value, the ion core saturates, and large increase in IS gives us small increase in G, the flux. So we get a disproportionate increase in the IR losses due to the larger IM, because you are increasing the current, the flux is not increasing, and that means a high amount of current will be flowing. So the I square losses will increase as a result. And we get harmonics in the current, causing extra IR losses. Because the core is saturated, there'll be harmonics components introduced because of the saturation of the core. So that will bring in harmonic current. That current is not useful. So that will increase the I square losses too. And we also get extra losses in the ion, because of the harmonics. They are at higher frequencies. So if they are higher frequencies, that will increase the ion losses, because we know that the eddy current and hysteresis losses depend on the frequency. So if they are harmonics, then they also increase the ion loss. So that means that you want to ensure that the flux is no more than what the rated, so that all these issues will not be happening. So we therefore control the flux to be its rated value. So the rated magnetizing current is usually much smaller than the rated rotor current. So when you compare the rotor current and then the magnetizing current, the rotor current is higher than the magnetizing current. So this keeps the stator current also low, because the stator current is the vector sum of Im and the Ir, but in terms of magnitude, it is Im squared plus what? Square root of Im squared plus Ir squared. So if this is small, that means that this is the stator current is also going to be kind of the same as the rotor the rotor current. So meaning that the losses will also be low because of the low current that will flow. So at flux level below the rated flux, more total stator current is required for a given torque, therefore increasing the copper losses and reducing the maximum torque capability of the drive. So we know that the torque is proportional to this, right? So if you also reduce the flux level to, because we know that if you increase it, if you want it to go beyond the maximum, the IM is going to be high and that will increase losses. If you also want it to be reduce it, you also need a high torque to be able to maintain what? Like if you want to a high torque, because the flux is low, if you want a high torque, that means that the current must be increased. So if you increase the current, that also increases the losses. So we have to always ensure that the flux is at the rated what value. So that is what the third point is saying. So the flux levels below the rated value requires more stator current for a given torque, therefore increasing the copper loss and reducing the maximum torque capability of the drive. So we are trying to understand why we need variable voltage. So therefore, for most applications, it's desirable to operate at the rated flux so that the iron loss and copper loss at the rated are minimal, because you know that when we increase the flux, when we want to go beyond the rated flux, it increases losses. If we also go below, it also increases the losses. So the point that we can have minimal losses will be at the rated. So we operate at what? The rated flux. So for the flux to be at, for us to get a rated flux, that means that the IM must be constant so that the flux will also be constant at the rated value, right? So we have to IM must therefore be controlled to be constant at all frequencies. So if the frequency is variable frequency, so if you change the frequency, you want the IM to still be what? The same, so that we'll keep the flux constant at the rated value. So that is what we are trying to do. So when we go back to the equivalent circuit, we say that IM is what? Vm over omega E Lm J. So, but since we are interested in the magnitude, we just neglect this and we are going to have this. So here, we are going to have, this is constant, right? Lm is constant. So for Im to be the same, the change in this one should also be proportional to the change in the speed, the omega E, so that so that Im will always be constant. So Vm must be controlled to be proportional to omega E. So when you change the speed, that is the frequency, the Vm also changes by the same proportion so that Im will remain constant. So that's why we need a variable voltage. So because as you are changing the speed, if you want to change the speed, definitely omega E will change. So you also want that the Vm should also change by the same proportion to keep Im constant and so that we can also operate the motor at the rated flux. So at high values of Im and omega E, the voltage drop across the stator resistance and the leakage inductance, which is given by this VRL, is very small compared to Vm, and therefore we can make assumptions that Vm is almost the same as the supply voltage, right? So if the drop across the rotor resistance, the stator resistance and the leakage inductance is very small, because Vs will be VRL plus what? Vm. If this value is very small, then we can say that it's almost zero. So Vs will be approximately equal to Vm. So that is with the assumption that it's very small, right? So if Vm is almost the same as Vs, then To control VM, then we can control the supply's what? Voltage. So we control the supply voltage, and it should be proportional to omega E. So that is what we are going to do. And this leads us to the variable frequency control, right? So a voltage applied, the voltage that is applied is proportional to the frequency. So you apply a voltage that is proportional to the frequency so that you can keep Im constant to operate at the rated length. So this is why we need a variable voltage. So above the rated speed, Vs is held constant at its rated value, resulting in field weakening. Because we know that field weakening happens when you want to operate the machine above what the rated speed, which is the base. So beyond that, if you want, when Vs is at its rated value, you can't go beyond that. So if you want to extend the speed range, then you have to reduce the flux so that when you reduce the flux, the speed will increase by the same proportion. So that is what is happening here. So we come back. So now this is constant. If you want to increase this, then you reduce Im. So you reduce Im to be able to extend the speed range. So that is what happens at field weakening. And we will have these graphs at this point. So field weakening at high speed. So you realize that when you go beyond the speed and you want to do field weakening, you have to reduce the field, and realize that the curves begin to reduce, and that is where we have field weakening, and that is the constant power region. So in Vs equal to K omega E, K is such that the rated voltage occurs at K is, so if you want to know K, this K, we use the rated values to determine it. So if the rated voltage is 415 and the speed is 50, then use that to get your K and ensure that this particular voltage that is applied is always given by the same proportion. So we are going to use proportionality at this point. So if V rated is the maximum voltage of the converter, then Im and the field must reduce if we wish to operate, extend the speed range. So that leads to field weakening, and we will operate in the constant power region, right? So frequencies to about twice the 2 omega are normal. And this is employed if the load also has a constant power characteristic so that good motor load torque matching can be done. So you can only extend if you get the best performance when the load is constant power load. So that is about the field weakening. So that one was at high speed, right? So we look at the low speed operation. So at low speed, the voltage drop here is very significant. So you cannot make an approximation that Vs is approximately Vm. You can't make that assumption, because when you make that assumption, you are going to be wrong. So how do we do it? So, but we still have to maintain. Vm over omega E. They should still be proportional, right? So even if Vm, they should also change by the same proportion, right? So Vs must be boosted to maintain this one. So at low speed, you boost Vs. So we add a boost voltage. So we have the boost voltage that is added so that we can still keep the same relationship. So that is what you do. So at low speeds, you add a boost voltage so that you can keep Vm over omega E constant so that you can still operate at constant Im. Any questions? All right. So let's continue. So the torque speed characteristics of a variable frequency drive will definitely be similar to the induction torque speed characteristics. So the variable drive operates in the linear region, right? So we mentioned that in the linear region, the slip is very small. So the torque equation will be given by this. So that is what we are going to do. So this is the expression that we have. Am I still in the meeting? Let me see. Like this. We are not muted. Please let's continue. Okay. So since it's operating in a linear, the slip is very small, so it will be governed by this relationship, the torque. Be governed by this relationship. So this is what we are going to use for this will be the torque speed relationship. So we can see that the torque is proportional to the slip, the omega slip. All right. So let's look at different speeds. So when you operate at different frequencies, and then what we are going to have. So these curves here, they have at different frequencies, right? So this is at different voltage, different frequencies. So we see that they are proportional. So that is what we can see. They are proportional. So you realize that the red, this one is for 50 hertz, 400 volts. The second one, okay, I don't know the voltage and then the speed. This is for 25 to 100 volt. So that is what we are going to have. So you see that they will all operate in their linear regions. So with this, we can reduce the voltage. When you reduce the voltage, we reduce the frequency, and then you still see that it will operate in the linear region. So these are at different speeds and then different voltages, right? And it will operate in the linear region. That is what you are going to do. And this one is showing us the constant torque and then the field weakening path that will lead to the constant power region, which I believe we are familiar with. We saw this in Unit 1. Okay. So if we control Vs to be proportional to omega E, then we have a constant flux operating at most speeds and a series of torques. So realize that the flux is constant at different speeds, and then they torque to. You also have different torque speeds characteristics, but it's at the same flux. So that is what we want. So it will be in the linear regions, right? So when we look at the torque speed characteristics of induction motor, this side is the motoring, and then the other side is the generation, right? So we have motoring and then generation. So this represents the generation, and this one represents the motoring. So at different speeds. So we look at the variable frequency open loop. So we have this RF frequency supply. So this is the one that's able to generate the variable voltage and then the variable speed. So this one is basically it to be a power electronic converter. So we've seen it already. You have a rectifier with connected to an inverter to get as variable voltage and variable speed. So that is connected to an induction motor, and we have to now um, give our reference for speed. So when we give our reference speed, this is a reference you want. It will go through rate of change speed limiter, give us the speed that we want. So this is omega E, and we need to pick this omega E and pass it through a function generator to generate a proportional VS as a control signal to the power converter to give us the speed and then the voltage that we want at this output, which will be fed to the induction motor. So this is the open loop control. To realize that this one, we are not taking feedback. There is no feedback here. So this is open loop. So use the fact that the slip is more at rated torque. So that is for about 10 kilowatts of power, and it's less than 1% for 10,000 kilowatts per hour. So if the slip is very small, we can say that omega R is almost omega E. So when you change omega E, changes omega R. So that is the approximation here. So that is the approximation. So that is the open loop control. So no speed feedback is required. The dynamic response is slow, so we must include a rate of change limiter for the speed to prevent the slip from increasing beyond its rated value. So high slip will cause an overcurrent. High slip will cause an overcurrent because at that point the flux it is going to affect the flux levels. So this is what RR over X. So if this is increasing, this value is basically reducing. So if you look at IR, we are saying that it's VS S over R. So if this is increasing, what I is also increasing. So that's why you're saying the high flux will cause an overcarrying through. Okay, so this from this relationship. So this is based on the steady state equivalent circuit and not considering the motor dynamic response. So we're just looking at the steady state operation of the motor, not considering the dynamic response. So the speed drops by a small amount with load because of that. Because when you load it, the speed is going to reduce up to the rated slip frequency. So we have to improve that by getting the closed loop speed control with slip compensation for the variable frequency drive. So this one incorporates speed measurement and feedback. So it works on the principle that the torque is proportional to a slip frequency, which we saw already. T is proportional to omega slip. So that will be proportional to S omega E. So that is what we are going to use. So the deviation of this scheme is based on the steady state analysis, which is not valid under rapid changing conditions. That is, the dynamic performance is very poor. So this is still based on the steady state performance. So more complex control schemes have been developed based on the full transient representation. So you model everything, include all the dynamic performance parameters of the motor to get that done. And these are known as vector control schemes and achieve better performance than the equivalent DC drives. So that is for the frequency control. So for that one, we are going to put in compensate for the if we we'll measure the output. So there is a feedback ATACO generator to measure this one. We bring it and we measure it with the reference that we want. So this one, you're actually measuring the actual output. So you generate an error signal, you pass it through a controller, and you ensure that the TE that you have, so the output is going to be TE, which is the torque that is required, and you ensure that it's almost the same as what the omega slip. So we know omega slip plus what? Plus omega R will be equal to omega E. So that is what is happening here. So this omega E is equal to omega slip plus omega R. So you can see that this is omega R. So that is what we are going to have. Then pass it through a function generator to generate and a VS that is proportional to ensure that the IM is what? Constant. Then you feed it. So that's the difference between this open loop and then the closed loop speed control of the VF drive. So that is the theory, right? So practically, how can we realize it? So we use pulse width modulation to create a variable AC voltage from a fixed DC voltage. So because we want the output frequency to be variable, output voltage to be variable, then we can use we can do pulse width modulation to create that. So definitely we will need an inverter for that purpose. So that is high frequency switching. So typically switch from 0.5 kilohertz to about 20 kilohertz. So that's what you do. And fixed switching frequency depends on the output power. You can also do fixed switching frequency. That one depends on the output power. Or you do duty variable duty cycle. So you vary the duty cycle, you fix the switching frequency, and you vary the pulse. So that is the PWM that we are talking about. So you use a diode rectifier to create a DC link for the AC means. So this one is an uncontrolled rectifier. So you put a diode rectifier, you take the AC, you rectify it to DC, and you invert the DC to get a variable AC and variable frequency. So practically, this is what it looks like. So this portion is the DC, the rectifier, which is the diode rectifier. So you take your mains and then you convert it to DC. So we have this as a smoothing inductor, and so we have a capacitor to also smoothen the voltage as well. And this portion represents the PWM. Right, so this is the PWM inverter. So that is what we have here. So it will give you a variable frequency to give you also variable voltage. So that is what we have here. So this is three phase, this is also three phase. So we have each leg producing a certain voltage. Right. So the voltage source inverter or voltage fed inverter or variable frequency, variable voltage supply is the same thing. So the front end is a diode rectifier, which you've seen, and the inductor helps to protect during the startup, so to limit the inrush current. You know that when the induction motor is starting, it draws high amount of current. So you use the inductor to limit the inrush current. And that inductor also helps limit the current during the shoot through. So that is when one thing is about, like, you see that they operate in things, right? So if you want to turn off this and then this one is turning on, realize that it can kind of like create a short circuit. So even if that happens, the inductor is there to still protect the circuit and limit the current so that it's not dangerous to the machine. So when both IGBTs in the leg are turned on together by accident, and the capacitor acts as an energy store to provide high frequency current harmonics. So that is what the capacitor is doing. And this is the PWM that is produced, and we have this as the AC signal that is produced at the end. This, I think we looked at this in power electronics. So this one is just showing different implementation. It's the same thing we have here. So the variable voltage and speed, that is omega E, are synthesized by modulating the transistor switching pattern. And this is called pulse width modulation, or PWM. So these are the pulses that are sent. This is how the switches are turning on and off. So how to generate this waveform is, I think we studied it that in power electronics. So, and that gives us the output waveform with some harmonics. Definitely there'll be some harmonics. So the power transistors are switched on. These are the switching frequencies that we have, and omega R might be positive or negative depending on the phase sequence of the voltage supply. So if you change the phase sequence, definitely it will rotate in the opposite direction. So that's what this point is saying. And when omega E R is greater than omega E, then it will be doing regeneration. It's now acting as a generator. It's not a motor EV. So what happens is that the current is going to reverse its direction. So it will be moving from the motor side rather to the supply. So that is what is going to happen. So we have the IDC current reversing, right? So that is what will happen. So the current that is coming will be charging what? The DC link capacitor. So because of that, its voltage is going to increase. So to reverse the speed in motoring mode, simply change the phase order. We've seen that. So how do we change the phase order? So phase, we know normally, usually phase A leads phase B, B leads C. And so when you reverse the order, A will lead C and C will lead B. So when we do that, you've reversed the phase order, and you've reversed the direction of the motion. So it will now be operating like a generator. Only when the load speed is above what? The omega E, what is the synchronous speed. So at that point, it will be regenerating, and the phase going to be 180 degrees out of phase with respect to the phase voltage. So the current direction is going to reverse. That's what they are saying. And there is a large energy transfer to the capacitor, and its DC voltage is going to charge up. So something must be done to prevent the VDC from rising uncontrollably. So we have to find a way of protecting the capacitor. If the voltage goes beyond a certain value, the capacitor can do an even burn. That is so. So this is another way of representing. It's the same equivalent circuit. So if the current is moving this way, it's motoring. If the direction reverses, it is doing regeneration. So that is what you're talking about. And this is the capacitor that it will be charging, because the diode will not allow the current to reverse back to the supply. So the only part for it is to be charging the capacitor. That is when it is doing regeneration. So one way to prevent the voltage from rising above the limit is using dynamic braking resistor. So you introduce a resistor and you add a switch, so that when the voltage goes beyond a certain value, then you turn on this switch for the capacitor to discharge through the resistor. So the resistor will just be dissipating the energy. So when the regenerative current causes the DC capacitor's voltage to rise above a preset value, power electronics switch discharges the capacitor through a large resistor, and the resistor acts as an energy dump, and regenerative energy is dissipated in the capacitor as heat. So this is used when only generating that occurs when the drive is decelerating to 0. So you don't just use it in like that. So this is called dynamic braking. So you set a limit. So when it goes beyond that, then you turn on the transistor. When it falls below that, then turn off the transistor. So this is cheap, but it wastes energy, especially when you are doing a lot of braking. So we don't want that to happen. So another way we can do is, so that is one way. The other way is you can do PWM, use PWM rectifier. So you change the direct rectifier to a PWM rectifier, which is basically like the inverter. At this time around, it's allowing power to flow back to the supply. So this is what we call the active rectifier. So this is the PWM rectifier or the active front end. So this one, it draws sinusoidal current from the supply and can inject reactive power into the supply. So because of that, we need to put line inductors to decouple the PWM out from the system so that we don't have inductive power injected into the supply. So let me see. I think we still have some things to cover. So that is how you protect the capacitor during regeneration. So we know that the IGBT acts as a switch and requires a logic signal to tell you to turn on and turn off. And it requires a gate drive to amplify the logic signal and switch the IGBT on or off. So we need to create a pulse range for each IGBT to tell it when to turn on and when to turn off. So the pulses are switching at a certain frequency, at a fixed frequency, but the pulse width needs to be changed. So the switching frequency is the same, but you change the pulse width. So let's see if this is the switching frequency, it's constant, but the pulse you just vary the width of the pulses. Just so that is what is done here. Realize that if you check, well, let me see. Up to this, it's one switching period, right? Realize that over this time, you see that the pulses, the width of the pulses are changing. That's why it's called pulse width modulation. So you're just modulating the pulses to control the switching on and off of the IGBTs. And then you can filter this through extract, take out the harmonics, and leave the fundamental components. So when you do this switching, it comes with the fundamental components, and also it has harmonics inside. So the harmonics needs to be filtered so that we can get pure sinusoidal outputs. So the relationship between the amplitude of the modulation wave, that is the variable one, and the amplitude of the carrier, which is the fixed, is called the modulation depth, where the M is the modulation amplitude divided by the carrier amplitude. So asynchronous PWM occurs when the carrier frequency is fixed and typically switches between 0.5 kilohertz and 20 kilohertz, depending on the power rating. And the figure shows some waveforms. So here you see that this is the PWM signal that we see, the red one, and then the sinusoidal one is the one that we are getting here. So we just do the filtering to obtain the fundamental one. So this has harmonics in it, right? So the motor voltage and frequency are controlled by varying the pulse at PWM modulation depth and frequency. So that is how we are able to vary. When you vary the modulation depth, you are varying the voltage, and then you can also vary the frequency too. So the typical spectrum of the phase voltage will look like the one shown here. So when you view the spectrum of the PWM output signal, you are going to see this. So you are going to see a fundamental component with harmonics. So these are the harmonics that are present. So we have to filter out these harmonics and leave only what the fundamental component in there. That now goes to the induction motor. So how does the motor work with such an powerful voltage waveform? Well, we know that the machine is inductive. So it has inductance. So the inductance will filter out the higher frequencies and leave the fundamental components to go to the windings. That is what will be present. So the motor is inductive and its impedance at high frequency is high. Therefore, the voltage components associated with the higher frequencies give rise to much less current than the fundamental, and the machine reacts predominantly to the fundamental component. Therefore, as far as the machine is concerned, PWM voltage source inverter looks like a variable frequency sine wave source. So the resultant current is much better. Like it's almost like the sinusoidal one. So that is what we do. So this is how we practically implement the variable frequency and drive that we saw. All right. So the choice of switching frequency. So if you switch at when we have higher frequency, it means good motor current, but high switching losses in the power electronic device. So when you switch at when you have the higher frequencies, the inductance of the motor is able to filter those ones out. So making the currents much smoother. But because you are switching at high frequencies, it's going to increase what the switching loss in the power electronic device. And when you also switch at low frequencies, it means that the motor current is going to be poor, and there will be high power losses in the motor because of the high current that will flow, right? Because the current will have harmonics. So the harmonics in the current will lead to high losses, but the switching loss will be very small. So that means that if you switch at high frequency, you incur high switching losses. If you switch at low frequencies, the motor current is very poor, and there will be higher power losses in the motor. So you have to try and balance the two. So there is a compromise between the two, depending on the power device application, right? So if it is IGBT for 10 to 100 kilowatts drives, so you switch them between 2 kilohertz and 10 kilohertz. But when it's below 10 kilohertz, MOSFETs are used for that purpose because of the amount of power they can handle. And the frequency may be ultrasonic, that is much greater, a little greater than the audible frequency range, because the power is low, so you have to switch at higher frequencies. So that is what we have. So this is just a simplified diagram for multi-machine system. So you have one power converter that is feeding different induction motors. That is what we have at this point. So we also have the 4-quadrant operation in the induction motor drive. So this is an inverter. This one too is also it's a rectifier, but it's an active rectifier. It's able to allow it's an active rectifier. So it's converted from AC to DC, and then this one converts from DC to AC. So, but it allows power to flow in either directions, right? So it can allow power to flow so it can allow power to flow from the outputs this side to this one. It can also allow power to flow from the grid to the motor. So you can use it in wind turbines for power generation. And the speed too can also be varied, because when you switch the phase sequence of the induction machine, you change the speed. So this one is able to operate in all 4 quadrants. So that is what we have. That is 30. So we take a summary, and the next time we'll come and solve the examples. So about 25 to 30% of induction motor drives are driven by PWM converters. So the open loop variable frequency drive is the most common type. So about 60% of the total drive that are available. So many drives, especially pumps and fans, are just switched on and left running for long period of at constant speeds. So because the left at constant speeds, you don't want to, you're not, you don't need any um, feedback system to correct anything. So the variable drive operations based on it only control the RMS values. But the IM constant, that is the flux constant. But okay for just starting load requiring low starting torque and at low speed. So but if it requires low torque and low speed, using using the variable frequency drive work well. So we need to control the instantaneous values of current to get fast control of torque and flux, hence speed. So if you want to improve the performance, then the control, you need a closed loop control. So you have to implement the vector control of induction machines. So that is what you need to do to get that done. So in conclusion, the induction motor is the most popular motor for variable frequency applications. So because these are the reasons: the motor is rugged, spark free, and requires less maintenance. Variable frequency control is simple to commission, and its poor dynamic performance and close speed loading are acceptable for many applications. And IGBT inverters are now relatively cheaper and easy to use at power up to about 100 kilowatts. But a DC bridge draws poor supply current and high dynamic response requires additional complexity. So that is just a conclusion of the variable frequency drive. So these are examples. We will solve them later in the next meeting. I think we've spent quite some time. So we'll stop here. If you have any question, you will ask. Or let me just give us a brief summary of all that we've done. So we want to operate at, we want the motor to operate at the rated values. So flux should be rated. So in order to maintain the rated flux, we have to ensure that IM, which is the magnetizing current, is so constant. And IM is given by its magnitude is omega VM over omega E LM. We saw that this is a constant. So if you want to maintain this, then you have to, and omega E is the speed that you can vary. So when you change omega E, VMs will also change by the same proportion. So that is so why we need to vary the voltage. So we've made some approximations. We are saying that for high speed applications, the VM is almost the same as the supplies voltage. So if you vary the supply voltage and vary the omega E by the same proportion, then you ensure that IM will be constant. But if for low, so that we can keep VM over omega E constant. Flux, which is rated. So we needed to find a way. So that is it. So we looked at two ways of control the open loop and then the closed loop. So in the open loop control, voltage all these. Okay. Steph went here, okay, and we'll continue another time. So I'll end the meeting here. I didn't know that I was disconnected. So. All right, thank you.
That's why you were quiet for a while.
Pardon?
That's why you were quiet for a while.
But I'm not getting you.
No, I said I didn't hear you talk for a while, so.
I was
Right.
disconnected. That's why. Sorry about that.
Mm. Oh, no, no problem. But how are you doing?
Okay. Do you have any questions?
I have. So after the just the fundamentals of the induction motor, right?
Yes.
When we are dealing with the pulse width modulator converter, that
Yes.
section is the only part that I am not that okay with. But then we could meet another time, maybe personally, so that you can take me through as quickly as possible.
Okay. Okay.
Okay.
Have
Then
a
take care.
wonderful evening.
Pardon?
Since you have a wonderful evening.
Oh, you too. Take care.
All right.
Okay then. Bye.